Hi, my name is Dannells. I will be presenting our paper Supervised OCR, Post-Correction of Historical Swedish Texts. What role does the OCR system play? The work was carried out by Simon Persson and myself at the University of Gothenburg. Optical character recognition, OCR, is the process of converting images into digitized editable text. OCR techniques have been applied since the 90s, and the accuracy of OCR systems has improved significantly during the last decade, in particular for modern material with good print quality. For historical material, the quality of the results of the OCR vary greatly depending on the system that was used to process the image. To illustrate this, consider a sampled line of a scanned image, given with its ground truth text, and the results of three state-of-the-art OCR systems, EBI, Tesseract, and Corpora. As we can observe, none of the systems got all the words correctly. The types of errors the systems produce vary with respect to recognizing word boundaries and character confusion. To address the problem, post-processing computational methods are usually applied to correct the errors that were caused by the OCR system. However, current approaches for correcting OCR errors offer solutions that are tailored to a specific system. This can be problematic if the post-correction method was trained to overcome errors that were produced by a certain OCR system, but has to be applied on the results of another. For example, if the method was trained on the errors produced by Tesseract, but has to be applied to correct errors produced by EBI. Whereas OCR post-correction of historical text has received much attention lately, the question of what role does the OCR system play for the post-correction method has not been addressed before. And this is the question we hope to answer in this work. The kind of material we are dealing with comprises a selection of digitized versions of older facture prints from 1600 to 1800. The material was digitized by the Gothenburg University Library and the National Library of Sweden. It was produced with different EBI versions and was manually transcribed through double keying. What characterizes the material, making it challenging for OCR, is mixture of fonts, most notably Fraktur, Antigua, and Jabacher, mixture of typefaces, differences in font size, deterioration of the paper, variation in the language, and irregularities in print. Our aim is to develop a method that generalizes over the errors different OCR systems make and overcome and improve their accuracy results. Therefore, we OCR'd our material with 3 OCR systems and run some data analysis to examine the types of errors produced by each them in more details. We first calculated our character and word accuracy for each system to learn the differences in performance between them. As we can see, on character level, EBI has the lowest character accuracy with 58%. And the best results by Corpora are 80%. On word level, given in red, accuracy is 25%, for Tesseract 35, and Corpora 58. Which implies Corpora fails to correctly recognize approximately every second word, Tesseract every third word, and EBI every fourth word. We started off by analyzing the words that were recognized by each system. As the diagram shows, an apparent difference is the amount of words produced by each system. The amount of words produced by Corpora is 6 times as high compared to EBI and double as high compared to Tesseract. When we looked at the occurrences of non-alphanumeric characters in the OCR data, we find that also here the amount of words containing non-alphanumeric characters exhibit the same imbalance between the systems. Next, we compare the amount of vowels. The highest amount of vowels exists in the data produced by Tesseract, with nearly 80,000, compared to 12,000 in the Corpus data. We also compare the words containing more than one uppercase letter, and also here we find the highest number in the Corpus data, which is twice the amount of uppercase letters compared to ABI. This analysis suggests it might be beneficial to capture those differences in our method. We further looked at the word length distribution in the text produced by each system. The results show the majority of words recognized by all three systems are 4-character long. 6, 7, and 8-character long words occur relatively frequent. A smaller portion of all the words are 10 to 20 character long. Following previous post-processing methods, we divide the post-processing task into two subtasks: error detection and error correction. For error detection, we utilize a supervised machine learning technique. For error correction, we apply a simple Levenstein distance approach combined with lexicons and frequencies compiled from Corpora. There exist a number of different machine learning methods for detecting error words. One simple and flexible classification technique that has been known to be very efficient for correcting OCR errors is support vector machine. To our knowledge, this technique was not applied for correcting OCR errors of historical Swedish text before. In order to train an SVN model, we have to define a set of features to train the classifier on. Following our analysis, we decided to experiment with 6 statistical and word-based features, including the number of non-alphanumeric characters, trigram, character frequencies, number of vowels, word length, number of uppercase letters, and the amount of numbers occurring in the word. The next step is to present all words in the data according to this set of predefined features. And what we see here is an example from our training data of the 4 words, 2 error words and 2 correct ones. The label to the right is the one indicating whether the word is an error or not, a 0 and 1. For training, we computed over 104,000 feature vectors representing both error and words and correct ones. Correct words were extracted from the manual transcription, and error words were extracted from the output results of ABI, Tesseract, and Octopus. So we have a presentation from all 3 systems. For the error correction step, we applied Levenstein distance to search for candidates to replace the error word with. We rank these candidates based on their frequencies compiled from our Corpora and choose the correct word with the lowest Levenstein distance and the highest frequency. The word frequency list is compiled from pages from 1600 and 1800 from the project Runeberg, containing nearly 3 million words. In addition, we have a word list compiled from 2 lexicons, one 18th century and one 19th century, with over 530,000 words. We evaluated our post-correction method with the same method as we did to produce the baseline, but now we look at the character accuracy and word accuracy compared to the baseline in red. The character accuracy shows a minor improvement for Tesseract, but not improvement for ABI and Octopus. On word level, our system improves the accuracy results of Tesseract and ABI, but it actually harms the result of Octopus, which is the best performing system on our material. A further analysis shows the system performs best on short words up to 4 characters. The majority of these words are misrecognized by Tesseract, but are also covered in our lexicons. So the histogram in the middle showing the results from Tesseract, and the red area indicates how many are covered in the lexicons. And this is the majority of them are covered in the case of Tesseract. Back to the OCR example I showed in the beginning of the presentation, but now after we applied our post-correction method, we see that our method is able to remove non-alphanumeric characters and split long words into shorter lexical ones, but the selected words are not necessarily the correct ones. This is a typical real-world error problem where you find a lexical word, but this word is not correct in the context you are looking at. To conclude, the OCR system does play a significant role for the post-correction method. It should therefore be chosen carefully depending on the material. Our post-correction method excels at correcting specific types of errors, but developing a post-correction method that is not tailored to any particular OCR system is a great challenge. And there is still a lot to work on. In our paper, we give pointers to future work. And if you are interested, you are welcome to read it yourself. Thank you.